Okay, why don't we start? Good morning. My name is Changwan Ha from Microsoft Quantum team. I'm one of the researchers in the team. And I'm going to tell you, I'm going to give you a brief overview of what quantum computing is, what is it, and why we do it, and how we do it. So the first, we would like to understand what quantum computing is. Computing in general means that it is to manage and process and communicate information for various purposes. I don't want to define what information is, I just rely on your intuition. So let me give you what one of the first general purpose computer looked like. It is an ENIAC installed in Pennsylvania back in the 40s. And it was designed for the purpose of calculating the trajectory of a ballistic missile. And then the first program it ran was actually not about that ballistic missile, but about some nuclear physics calculation initiated by the John von Neumann and others for the Manhattan Project. So it was calculating some physical process, actually. Now, with the invention of transistor, the machine got so smaller and so much faster, and the physical reason that the physics that enabled this technological innovation was based on quantum physics. But quantum computing is not about that quantum physics here. It's more of a fundamental level. So what is that? So to give you an idea, let me begin with probabilistic computing. What is a probabilistic computing? Let me give you an example. Say I give you a function that's defined on 100 variables, and I ask you to find the integral of that. How would you do that? It's 100-dimensional, so if you make a fine mesh along, say, 100 mesh points along each direction, then the number of points you have to sample would be 100 to the 100. Astronomical number, you shouldn't do that. But more straightforward way is that you randomly sample points and then take the average. That will give you a very reliable estimate of the integral. And for all practical purposes, that's the best we know. Another random algorithm is that if I give you a black box of a function, a polynomial function, I guarantee that this function is a polynomial in, say, 100 variables. Then how would you say this is non-zero? Well, if I don't tell you anything about the function, then the only deterministic algorithm that we know of is essentially going through all possible inputs. There will be like, well, if the x1 are binary variables, then there will be 2 to the 100. So you shouldn't do that. But the probabilistic method is that you just randomly sample input points and test if it's 0. And surprisingly, there's no deterministic algorithm is known for this problem. Another probably practically useful algorithm is that if I give you a factorization of one matrix C into A times B, then how would you check that the factorization is correct? Well, you could do the matrix multiplication, and that will, in practice, close to the n cubed complexity. But randomized algorithm can do it faster because you can randomly sample an input vector and then check the output of the two equations. And if you do it sufficient many times, then you have a high confidence that the equation is correct. And that's good for all purposes. So theoretically, we can imagine this probabilistic computing in this way. We start with just a flat distribution over some number of variables. And then my algorithm transforms that distribution under the classical rules. And we end up with some concentrated distribution that is hopefully concentrated around the desired solution. This is what's going on. Now, observe that the probability space, the space of all probability distributions, not the individual entity, it has exponentially many entries. And in any probabilistic computing, we don't keep track of this probability density function, but we just work over examples. Similar principle carries over to the quantum computing. The difference is that you take square root. So if I had a bit, then there will be two numbers. Well, actually essentially one number, because I am constrained to the condition that the probabilities had to sum to 1. And I can denote that probability as a two-component vector with the positive reals. In the quantum computing, we take a square root. So each of the entries, the state of my square root, space of square root probabilities will reside on the complex numbers. And each entry takes values in a complex number whose modulus is between 0 and 1. And with a rule that the amplitude squared is equal to 1. Here the amplitude is a technical word to mean the square root of probability. So that's qubit. And it is apparent that if I have n qubits, then there will be exponentially many complex numbers to describe that distribution. However, in analogy with the probabilistic computing, we do not keep track of each amplitude. We shouldn't, because there are too many. And some fundamental feature of the quantum physics relates the two models. So if I start with some quantum amplitude vector, if I look at it, look is a rather not too appropriate, but that's most close term in the layman's word. If I look at it, then I would get the outcome 0 with the probability given by the amplitude squared, and probability 1 with amplitude given by this with a probability given by the amplitude squared again. And in a sense, this fundamental property of quantum physics limits our ability to use the quantum physics, because we're back to the probability instead of the world of amplitudes. And to exploit that quantumness, here are the elementary gates. Unlike the classical circuit where everything can be generated by NAND gates, there are several in the quantum case, but not too many. There are only, well, I listed actually over complete set. I only need this much, this, and that one. You can omit that one, for example, because this one is an application of twice of that. And the one notable feature of those matrices is that they are all unitary. Why unitary? Why do we need a linear algebra here? So the fundamental feature that quantum measurements maps up amplitudes to probabilities, we shouldn't measure them. We shouldn't collapse them. We shouldn't intervene the intermediate step of quantum computation. Well, if you do so, then you are back to the classical probabilistic computing. And you are not exploiting the quantumness here. So we shouldn't look at it. And the only way to not look at it but somehow operate is to go through the unitary operation. And therefore, we have a unitary set. And I want to emphasize that unlike some popular social media exploits it, quantum is not so real in the following technical sense. In the probabilistic computing, I'm repeating myself, it was all handled by the exponentially many positive real numbers that sum to 1. Taking the square root, you end up with exponentially many complex numbers whose modular squared sum is 1. And quantum circuit is nothing but a unitary matrix multiplication on that gigantic vector. Therefore, a logician would say, oh, anything that can be done with a quantum computer can be done on a classical computer. There's no in principle difference. Anything that can be decided in a classical computer can be done in quantum and vice versa. However, as a computer scientist, not every finite things are equal. Some things are much harder because you have to go through many more steps to accomplish the job. And that's where the quantum computing is. So why do we care about the quantum? Because it can sometimes address classically intractable problems. And I'm giving you 2 or 3 most famous examples here. So there are quantum algorithmic primitives that we use over and over again. We are waiting for a new primitive, but so far these are pretty much complete list. So probably the famous one is the first one. The search over the database of n entries can be done in square root time instead of looking at n entries. There's a quadratic speedup. And a similar principle can be applied to the sampling problem where your accuracy converges much faster. Instead of in order to achieve the absolute accuracy in your statistical measurement, then you have to go through 1/epsilon squared number of samples to achieve that goal. But in a particular quantum setting, that accuracy convergence can be made quadratically faster. And the Fourier transform, which typically, in the classical world takes about n log n time, where you have a n component vector, this becomes exponentially faster. You lose, you forget about that n vector, but left with a log n vector. And certain aspects of linear equation can be obtained exponentially faster in the dimension. If you have a matrix of condition number kappa, then classically you need n square root kappa number of operations to calculate something about the solution. But quantumly, the dependence on the condition number remains, but the dimension factor, dimension dependence gets exponentially better. But note that all these primitives are applicable only for the data that are generated on the fly. It cannot be used for real data for a simple reason. It takes linear time even to load the data. So there's a bottleneck. However, there is a exponential speed up in the case of for the user-defined data when it comes to the simulation of quantum physics. So remember that ENIAC was first used to simulate classical physics. Now quantum computing is natural to solve problems that involves simulation of quantum physics. And this exponential speedup is very typical and natural. So what can we do with that? The one appealing example is the following. You may be surprised that the ammonia molecule consumes, the production of ammonia, it consumes like 5% of all global natural gas consumption, or like 2 or 3% or 1 or 2% of all global energy consumption. Because this chemical process at the industrial level, it requires like hundreds of degrees of temperature and hundreds times the atmospheric pressure. So to make that environment, you need a lot of heat. And surprisingly, there are some bacteria at the root of some vegetable that does this job at the room temperature at the natural atmospheric pressure. And after several decades of research, actually we don't know why. Slightly more in depth, the bacteria has a special enzyme, and in the middle of that enzyme there lies this particular molecule, iron molybdenum cofactor it's called. It's not too complicated molecule. It involves like hundreds of atoms. It's not terribly complicated. And this molecule is believed to be the key for this process that converts nitrogen molecule and combine with the hydrogen and to produce ammonia. And to understand how this works, we need to compute the energies of various chemical configurations. And that is computationally limited. Even the fastest supercomputer is not sufficient to address this problem. And you may expect that some experiment will tell us how this molecule works, but it is still crude. Maybe this process involves like several tens of steps, each of which is hard to compute, and we don't know how it happens. If we understand how it happens, then there's a good chance that we can utilize them and make the ammonia production much more efficient. And some estimate, some very scientifically reasonable estimate tells us that even very small scale quantum computer can help us here, like one that has only 200 qubits or so may be able to help us understand how this molecule works. And another famous example for the application of quantum computing is the factoring problem. Almost all cryptography practical protocol relies on the hardness of factoring. If I give you a composite number and don't tell you about the prime factors, then it is hard for you to figure out what those prime factors are, and based on that, we build out the public key encryption schemes. And if you have like I say, 100 cores in a classical computer, then merely factoring 1,000-bit numbers takes about order of a year. And if you increase that number to a 2,000, then that will take order of the age of the universe to compute, extrapolating the current technology. But if you have a quantum computer that has thousands of qubits, then that problem can be solved in the order of days. Well, this is due to the exponential scaling. You see initial gap here. For smaller sizes, quantum computer will not be of help because of the huge constant factor. I will get to that huge constant factor later. So if we then this poses a great problem or great concern to the world of cryptography. If the current technology is it will be broken by a quantum computer, what should we do? The quantum physics helps again here. There is a private key distribution protocol based on the quantum physics in such a way that any eavesdropping will be detected and is guaranteed by the laws of physics. And it inherently uses the quantum correlation, so-called entanglement, and robust implementation is still being developed. And to protect our information in the post-quantum era in the future, there is a quantum-resistant classical crypto methods, and there are candidates. And it will replace the current public key crypto systems based on the factoring. And with a requirement that it should be interoperable with the existing facility, the quantum private key distribution is not considered in this proposal, and such a purely classical algorithm is now being standardized by NIST. I heard that it is at round 2, where like tens of protocols are competing with each other to find the best one. So that was major applications or easy to access applications of quantum computing. Now, how do we make one? What are the challenges and where we are now? There are many abstractions in the architecture of a computer, in any computer. There should be a hardware that actually operates something, and there should be some programming support to control that hardware. And on top of that, we have to think about what algorithms can we learn. And at Microsoft, we have investment in all stages. And how to make one in this talk will be focused on the hardware side. And you will hear more about the quantum programming side today later. So there are many qubits proposed, developed by the various industrial companies. Some are based on the photon, its polarization. Some are based on the superconducting devices, and you take a very particular physical states in this device. And some are thinking about the quantum dots, where you isolate very tiny atoms or artificial atoms in your lab. Some are thinking about the atoms that are trapped in an optical lattice. We are thinking about a topological qubit. What is a topological qubit? That may sound scary, but not so much. So let me tell you a bit more about it. So to motivate, let me give you the classical error correction, the overhead. Well, let's talk about the classical error correction overhead. Here is a picture of deep space probe that we have to communicate over. And the communication is very noisy. You can't really hear the clear sound over that probe that are in the deep space, well, not light years, but it takes for light to travel, it takes about, I don't know, a few hours for the light to travel to that probe. So imagine that each bit you send is corrupted by the other bit. Your bit is flipped with some small probability. Then you can correct those, you can fight with those noises by make redundant message. So you send 0, 0, 0 in place of 0 and triple ones in place of 1. We say that these bits are physical bits that are actually sent, and these bits are logical bits that we meant to send. Now, the receiver, which can be the probe or us, decodes potentially corruptive data. If I receive 000 or two zeros and 1, then I would infer that message was just 0. In the other case, I infer the message to be 1. And that's reliable because the logical error probability, that is, I inferred it was 0, but the sender actually meant 1, or vice versa. That logical error probability gets smaller for a given physical error rate by this repeating procedure. And if you do it more clever, well, if you do the analysis, then given the physical error rate, the number of actual physical bits that you have to send as a function of this physical error rate, given the target logical error rate, scales like this. So as long as your error probability is less than half, then you can send some information, but the number of actual physical bits that you have to send increases quite rapidly if your physical noise is high. Exactly the same thing happens in the quantum world too. So even though we are dealing with the quantum information, the square root of probabilities, we can fight with errors by encoding our quantum information into the correlation of quantum particles. And there exists a quantum error correcting code in as much as we have a repetition classical error correcting code. And the similar analysis tells us this figure. If you want to achieve logical error rate to be 10 to the minus 10, here the error rate is the probability that the qubit is corrupted given a clock cycle, or a message if you wish. If we wish to achieve this very small logical error probability, then if your physical error rate is, say, 0.1%, then you would have to deal with thousands qubit. You have to send, you need 1,000 qubits only to send 1 qubit. But that number dramatically decreases if the physical error rate is decreasing. Now note the difference. In the classical world, the threshold below which we can send any information was half, 0.1. In the quantum case, it is order of magnitude smaller. And that's the challenge we're facing. That's why we do not have a general purpose quantum computer yet. So it is critical for scalability to achieve low physical error rate. Otherwise, the overhead from the error correction will be too large. And here comes, well, and that differentiates our approach from more conventional approach. One of the prevalent technology to build a qubit is based on the superconducting circuits, and they have error rate around here. So you will need approximately thousands of qubits to make a general purpose quantum computer. But topological qubit, if we have one, it is expected to have much lower error rate, hence much smaller overhead from the quantum error correction. That's why we are focusing on a good qubit. And that is very analogous to this picture. if you have a chalkboard, and you write something, here the writer was counting something, obviously. The small particle in your chalk is attached to your blackboard by some very weak chemical bond or friction, but it can be easily washed away. It doesn't really have a correlation between among the two, and it doesn't fight with noise anymore. But if you count using knots, as the old Incan did, then it can last for thousands of years. Because as long as the string is unbroken, the fact that there is a knot is an invariant. So topological qubit, conceptually, at a very abstract level, does the same job. So here's an actual example where that autonomous correlation helps. This is a figure from a 1980 paper where they measured so-called Hall conductance across the sample under a low temperature and a high magnetic field. And they just measured the resistance of that sample across a certain configuration. What they found was that there is a plateau in the resistance that are pretty wide and resilient to external parameters. They tested various geometries and various other settings. They even altered the current you're sending, and they didn't see any change. And this accuracy is so remarkable that it is for for a long time used as the calibration standard. Whatever sample you make, how dirty you are, it doesn't really matter. The autocorrelation among the electrons gives you robustness. And we want a qubit that exhibits a similar phenomena. So there is a proposal, theoretical proposal, that signals that, if you fabricate such a device by putting some very small wire on top of very special material in a low temperature and apply certain magnets, then there will be some hidden states that we can use to build a qubit. And one signature for that purpose has been experimentally observed. So we are optimistic that we will be able to find a material and setting such that the many-body electrons help us to build a qubit. And that's what we are focusing on. That's how we are going to build a quantum computer. So let's recap what I have said this morning. So don't be scared about quantum computing. It's just a square root of probabilistic computing. And to make use of that quantumness, we should remain in the space of amplitudes instead of probabilities. And that's why we should use the unitary operations instead of other classical analogs. And naturally, this quantum setting can simulate quantum systems efficiently, whose job is intractable on a classical computer. And therefore, quantum computer will likely have applications in the quantum chemistry and material science. And on top of that, there is some computational problems, including the factoring, becomes much easier on a quantum computer. And the quantumness is more subtle than, more subtle than the classical counterparts. So to overcome the overhead from the error correction, the physical qubit's fidelity is very important. And we are focusing on a very good qubits instead of many. And our quantum program covers every aspect of that, from hardware to intermediate programming language, to higher level algorithms, and others. And you may wish to check out our websites that illustrates further conceptual explanations and our programming tool sets. And you will hear more about it later today. And I'm ready to take your questions. Thank you.
So, how long do you think it'll take before you have a functioning topological qubit? Is it 1 year, 10 years?
Well,
You're not allowed to say.
I personally don't know. It's still under investigation.
So IBM has already functioning quantum systems in their cloud, but that's not based on topological.
Right.
It's the resonance, magnetic resonance, I think, or I'm not sure. So do you have any, is there any thought that that's what they're doing is any good, or is it?
It is an interesting device, and interesting in that you can actually implement some experiments and apply gates there. But it's only 5 qubits, or well, I forgot the exact number. Maybe I shouldn't say 5. But it's anyway a small number, and anything that can be done on their machine can be done on a simulator too, very easily. So scientifically interesting, and we'll see where it goes.
You had your example of the ammonia locking. So how is it that a quantum model helps us here? Is it a steady state, or because it doesn't give us anything with respect to time evolving in molecular dynamics, right?
Oh, actually, good question. In fact, quantum computer is much better to simulate dynamics instead of estimating static properties. However, but the time scale where the chemical reactions happen is far smaller than the other thermal time scale. So that's why we are asking about the static numbers there. And the quantum computer can help there too, because you can estimate the energy of intermediate steps. So, you know, a catalyst is like a financing. You will make a profit in the end, but to make that profit, you have to invest too much. And that's why some processes are too slow in nature. And the catalyst is like intermediate financing facility where you lend small money and then make a small profit, and you have to keep doing to reach the eventual goal. And how we lend money and where to lend money depends on the molecular structure. And the typical method would be, well, okay, here is my catalyst. To understand that, well, let me attach an atom here. How much energy do I get? And you need to calculate that. Oh, if I know that energy, then I can calculate the rate the chemical reaction happens along that direction, and you do it many times. Here, the bottleneck is to estimate that energy, and the quantum computer will facilitate that process. You encode your molecule into your quantum computer, and let it find the ground state, and you make an energy measurement. The classical method exists, but they are very crude.
So you're basically finding the global minimum in a high-dimensional function.
It is like that. Yes.
Okay.
Yes.
Thanks.
Yes. But it's much better than the combinatorial case because it is supposed to be a nature thing. So you can simulate what nature does in a quantum computer and find the ground state energy.
One more question. So I read a lot about quantum-inspired algorithms.
Yes.
As people talk about, as quantum computing will overtake classical computing, then they keep, especially in computations, they thought there were no fast classical solutions. Quantum-inspired algorithms keep popping up. Is that something that you see in your work and your research, looking for new algorithms that you run across quantum-inspired ones?
I think you will hear more about that in 10 minutes.
Oh, okay.
So I defer that answer to that talk.
Okay, thank you very much.